Hi, I'm Goh Zee Xin. I will do the demonstration of the project 1. So the project 1 is divided into two parts, which is part 1 MOSFET and part 2 CMOS inverter. So this one is the design according to the given inside the project file. M1 is NMOS, which is length equal to 0.25 micrometer, y equal to 2.5 micrometer. M2 is NMOS, where the length equal to 0.25 μm, y equal to 6 μm. M3 is PMOS, where the length equal to 0.25 μm and y equal to 0.65 μm. The VB is assigned to 2.2 watt. The Vin is varying from 0.6 watt to 1.2 watt, so we can change the Vin value here. Then this one is the SPICE directive. The first and second line is used for the SPICE level 1, and the second line is used to include the file TSMC SEM025 parameter text and input the TSMC180 library. The .P is used to simulate the operation region, and then .DC is used to simulate to get the VTC curve. So here we will simulate for the SPICE level 1 first. So here I will click simulate. So this one is the output get for the Vin equal to 0.6. So we can obtain the Vout at here. Then we can see the SPICE error log to see all the ID, VGS, and VDS of each MOSFET. And then we can do the calculation here to see for PMOS, NMOS, M2, and M1 to determine each operation region. So done for SPICE level 1. We will go to the second one, which is TSMC SEN2025. So we also click simulate. So this one is the operating output for the when using TSMC SEN025. So we can see the operation region through here for the TSMC SEN025. Third, we are going to simulate for the TSMC180 library. So this one is out of the TSMC180. Then we can go to see the SPICE error log. So this one is all the ID, VGS, VDS obtained for the TSMC180 for each MOSFET. So we can analyze the operation region for M3, M2, and M1 from here. Then I will change the Vin to my second step, which is 0.895 watt. And then repeat the same step, which is I will simulate for the SPICE level 1 first to get the operation region run. So 1.23 is the Vout for the SPICE level 1. Then we can see the SPICE error log. So here we can calculate the operation region from the VGS and VDS obtained for the M3, M2, and M1. Next, I will show to do the TSMC SEN025. So 1.485x7 is the Vout of the TSMC SEN025. Then we can see the SPICE error log here. So this one is the SPICE error log. We can get to know the M3, M2, M1, VDS, and VGS from here. Lastly is I will do the simulation for the TSMC180. So this one is the Vout of TSMC180. Then we'll go to the SPICE error log. So this one is the ID, VGS, and VDS of the M3, M2, and M1. Lastly, my third set is set Vin equal to 1.2 watt. So I will set my Vin equal to 1.2 watt. Repeat the same step. So the Vout is equal to 0.28 when using SPICE level 1. Then we'll go to the SPICE error log. So this one is the SPICE error log. We can get the ID, VGS, VDS of each MOSFET here. Then I will go to simulate for the TSMC SEN025. So this one is the Vout of TSMC SEN025. Then we'll go to the error log. So here is the here we can get the ID, VGS, and VDS of each MOSFET. Lastly, I will go to TSMC180 library. So this one is the Vout of TSMC180 design. Then we'll go to the SPICE error log. This one is the SPICE error log of the design. So we can see the VDS, VGS, and ID for each MOSFET here. Please take note that inside the manual calculation, we are assuming gamma and lambda equal to 0. But inside the simulation, we take account in the gamma and lambda, which equal to the given value inside the appendix. Next, we will go to the project part 2, which is to design a CMOS inverter using 0.25 micrometer CMOS technology with assuming NMOS in velocity saturation and PMOS in pinch-off saturation. So at here, I choose my NMOS Y is equal to 0.375 micrometer, and from my hand calculation, I get the Y of the PMOS is equal to 1.3 μm. And all the length of the PMOS and NMOS is 0.25 micrometer since we are using 0.25 micrometer CMOS technology. And inside my hand calculation, my desired VM is equal to 1.25. So at here, I will put one V in here, and at here, I'm putting one pulse input to generate V transient later. So this one is M1 is the NMOS and M2 is the PMOS. So as the same with the project part 1, the first two lines is used for the SPICE level 1. Inside our hand calculation, I'm assuming gamma and lambda equal to 0, but inside the simulation, I'm assuming gamma and lambda equal to the value given inside as the appendix. So the second line is used to include the TSMC SEM025 parameter tags, and the third line is also used .include to let us use the TSMC180 library. Then .op is used to generate the ID and operation region. .tc is used to generate the VTC curve, and .transient is used to simulate the transient analysis. So at here I will run the simulation first for getting the operation point for spice level 1. So for the Vin, I will put Vin equal to 1.25. So I will run the simulation. So I'll get the Vout equal to 1.365. Then we'll go to the spice level log. So at here we can see the ID, VGS, and VDS of PMOS and NMOS. And then we can calculate the operation region for the PMOS and NMOS to verify our hand calculation result. Then second, I will do the simulation for the TSMC SEM025 parameter. So this one is the TSMC of the TSMC SEM025. Then spice error log. So at here we can obtain also the ID, VGS, and VDS for the PMOS and NMOS for us to calculate the operation region. Then we'll do for the TSMC180 library. So this one is the Vout of TSMC180. So we'll go to spice error log. Then we can obtain the ID, VGS, and VDS of PMOS and NMOS for us to calculate the operation region. Next, I will proceed to the simulation of .tc to generate the VTC curve for spice level 1. So this one is the VTC curve for spice level 1. And the VM is almost equal to 1.25 watt. So from the VTC curve, we can also get the VIL and VOH at the first stop here when stop equal to -1. And then we also can get the VIH and VOL at the second stop here when stop equal to -1. And then we can calculate the noise margin from the VIH and VIL then according to the formula. So next I will simulate for the TSMC SEM025. So this one is the VTC curve of TSMC SEM025. So the VM is here, which is around 1.62 watt. And then we can also get the VIL and VOH at the first stop equal to -1 here. And then get the VIH and VOL at the second stop equal to -1 here. So next, I'll go to do the simulation for TSMC180. So this one is the VTC curve for the TSMC180. For the VM is also around 1.62 watt, which is almost the same with the TSMC SEM025 library file. So at here we can also get the VIL and VOH at the stop -1 here, and get the VOL and VIH at the second stop equal to -1 here. Then we'll do for the V transient analysis to get the V in and V out waveform. So I will first simulate for the spice level 1. So this one will be our waveform for V in and V out. So the bottom one is V in and the upper one is V out. So because it is CMOS inverter, so we can see the output waveform is the inverse one. So from here we can find the TPLH and TPHL. So at this one. So at here we can find for the TPLH for the spice level 1 design. And then at here we can find for the TPHL for the spice level 1 design. Then next I will simulate for the TSMC SEM025. So this one is the waveform of V in and V out. So the bottom one is V in and the upper one is V out. It is also meet the desired theoretical because V output is the inverse of V input. So at here we can find the value of TPLH. And then at here we can find the value of the TPHL. Next, I will go to do the simulation for TSMC180. So this one is the V in and V out of the TSMC180. The bottom one is V in and the upper one is V out. The design is also meet the theoretical where the V out is the inverse of V in. So at here we can find the TPLH. And then at here we can find the value of TPHL. So that's all for my video demonstration, and thank you.